Welcome to the deep dive. We know you're swimming in information, so our job is to cut through all that noise and give you what you really need to know, straight from the sources you provide. Today we're tackling something pretty big in the Java world, virtual threads. We've got the material you sent over, and we're going to unpack it. The big questions are, what exactly are these virtual threads?
Yeah.
Why is everyone calling them a game changer? How do they work under the hood? And,
Yeah.
what do you actually need to understand about them? I mean, think about it. Traditionally, hitting a few thousand threads could cripple an app. Now they're talking millions. That's a huge shift.
It really is. This is super important for anyone building modern software, especially thinking about scale. It changes the game for high-performance Java apps. So yeah, this deep dive will cut through the jargon, give you the context, and really explain what this shift means.
Okay, game changer. Let's break that down. What is a virtual thread? What makes it so different from the threads we've used for years?
Right. So virtual threads, they became standard in Java 21. That was JEP 444. And the absolute key difference, they are totally decoupled from operating system threads. Your classic platform thread maps one-to-one with an OS thread. Heavyweight, virtual threads, managed entirely by the Java virtual machine, the JVM. It's a totally different approach. It lets the JVM juggle, thousands, potentially millions of these lightweight tasks super efficiently. None of that OS thread overhead. For you, listening, the big win is just the sheer scale you can now achieve without falling over.
Okay, that JVM managed versus OS tied thing sounds like the absolute core of it. So what does that actually mean for developers day to day? How does it change how we build things? Why the big buzz?
Well, it changes quite a lot, actually. First off, they're incredibly lightweight. Like we said, no direct OS thread mapping, so they're cheap to create and manage. And that directly leads to massive scalability. Think web servers handling, I don't know, hundreds of thousands, maybe millions of connections at once, that kind of scale. But maybe the most revolutionary part is how they aim to simplify writing concurrent code. The idea is getting back to a simpler thread per task model. You write code that looks sequential almost, but it scales massively. No more super complex thread pool tuning, hopefully. And crucially, compatibility. They work with the existing Java APIs, your thread class, executor service. You don't have to rewrite everything from scratch. Now, why use them? Well, handling high concurrency is the obvious one. Web servers, chat apps, e-commerce, backends, anything dealing with lots of simultaneous users, they really do simplify things. That thread per task approach avoids a lot of the complex asynchronous patterns, and that improves scalability and throughput, particularly for tasks. Ultimately, it just reduces the mental overhead, abstracts away a lot of that low-level threading stuff. Think of it like this. Imagine you have like an almost infinite supply of tiny, super fast helpers for every little job. You just tell them what to do. You don't worry about managing them.
Okay, that makes sense. The what is clearer now. So let's get to the why should I care part.
Yeah.
What are the tangible benefits? You mentioned simplifying concurrency. That sounds pretty huge.
Oh, it is. And the benefits are really concrete. First, that scalability we keep mentioning. Handling potentially millions of concurrent tasks blows the old platform thread limits, maybe a few thousand, right out of the water. OS limits just aren't the bottleneck in the same way. Then there's the resource overhead. It's incredibly low. Remember debugging out of memory error because you had too many threads, each taking up a megabyte or so of stack space?
Oh yeah, painful memories.
Exactly. Virtual threads use a tiny fraction of that memory, much, much lighter, so you can have far more of them or just run more efficiently in constrained environments. And this leads straight into simplified programming. That thread per task model becomes practical. It often means you don't need to reach for complex things like, say, completable future chains or full reactive stream libraries, which, let's be honest, can be tricky to get right. What's really cool is how this lets you build really scalable stuff without necessarily becoming a wizard in advanced async programming. And they absolutely fly for IO-bound tasks, network requests, database queries. When a virtual thread hits one of those blocking operations, it doesn't just sit there hogging its carrier thread. No, it yields. It steps aside, lets the JVM put another virtual thread onto that carrier thread to do useful work. This keeps the CPU busy and boosts overall throughput dramatically. And finally, that seamless integration. Working with existing APIs, Spring, Jakarta EE, it lowers the barrier to entry. You can focus more on your application's logic.
That I/O handling, the yielding, that sounds like the secret sauce. So how does that actually work? How does the JVM manage this lightweight magic without tying up the OS?
Good question. Yeah, understanding the internals helps. So, platform threads, one-to-one with OS threads, dedicated resources, virtual threads, purely JVM constructs. They run on top of a small pool of carrier threads. And these carrier threads are platform threads, but there are only a few of them, maybe matching the number of CPU cores. Think of the carrier threads as the actual workers, and the JVM is incredibly good at scheduling virtual threads onto these workers. The core mechanism is something called continuations. It's a way to save the state of a running computation and resume it later. So when your virtual thread makes, say, a network call and has to wait, it hits a blocking operation. Instead of the carrier thread blocking, the virtual thread state is saved using a continuation, and it effectively gets parked off to the side. The JVM then grabs another waiting virtual thread and mounts it onto that now free carrier thread. It keeps the worker busy. There's a dedicated scheduler built on Java's fork join framework that handles this dynamic assignment. It's very efficient. Plus, their stacks are different. They don't pre-allocate huge stacks like platform threads. They grow and shrink dynamically, stored on the Java heap using way less memory. So, blocking operations become transparent. The virtual thread pauses, the carrier is freed, work continues, and when the I/O completes, the virtual thread gets rescheduled to resume. It's seamless. For you, the listener, the analogy holds. The JVM is the super efficient manager, the carrier threads are the few workers, and the virtual threads are the thousands of tasks being juggled. Worker pauses on one task, manager immediately gives it another. No wasted time.
Okay, like a hyper-efficient dispatcher, making sure those few workers are always busy if there's work to do. Is that fair?
That's a pretty good way to think about it, yeah.
And the beauty is, developers don't usually need to worry about continuations or schedulers directly, right? It's implemented within the thread class. You just create them with thread.aVirtual, or use that neat executors.new virtual thread per task executor.
Exactly. The goal is abstraction. Make it easy to use.
Right. So you've sold the efficiency and simplicity pretty well, but there's always a but, isn't there? What are the catches? The things we need to be careful about.
You're right, absolutely. It's not magic, and there are definite trade-offs and things to watch out for. First big one. Virtual threads aren't really for CPU-bound tasks. If your code is just crunching numbers nonstop, pegging the CPU, virtual threads don't melt much. Why? Because you're still limited by the small number of carrier threads, CPU cores. You don't get more processing power. They shine when threads spend time waiting. Then there's a really critical issue called pinning. This is probably the biggest gotcha.
Pinning. Okay, what's that?
If a virtual thread executes code inside a synchronized block, or calls a native method, JNI, and then performs a blocking operation while holding that lock or running native code, it gets pinned to its carrier thread. This means the carrier thread cannot be used to run other virtual threads while it's pinned. It basically behaves like an old-style blocked platform thread tying up one of your valuable workers. Too much pinning can kill your scalability benefits.
Ouch. Okay, so avoid blocking inside synchronize. That sounds important.
Very important. Use java.util.concurrent.locks. Re-entrant lock instead, as those are designed to work well with virtual threads and won't cause pinning when blocking. Debugging can also get interesting. When you have potentially thousands or millions of threads, stack traces can look different, and following the execution path requires different tooling and techniques. It's manageable, but it's a change. And while they simplify some aspects of concurrency, you still need to understand the fundamentals. Thread safety, race conditions, shared mutable stata, those problems don't magically disappear. You still need to write thread-safe code. Compatibility can sometimes be an issue too. Older libraries, especially those doing tricky things with thread local storage, might not behave as expected or might even cause pinning. Always test carefully. And finally, while they're lightweight, they're not free. Millions of virtual threads still consume some memory for their internal state and stacks, even if small. You can still overwhelm the JVM if you go completely wild without considering resource limits.
Okay, that pinning issue definitely stands out. And the reminder about thread safety is crucial. So pulling this together, what are the key pieces of advice for someone starting out? How do you use them effectively and avoid those traps?
Right. Practical advice. Number 1, focus on I/O-bound workloads. That's their sweet spot. Network servers, message queues, database interactions. Number 2, seriously minimize synchronized blocks that might perform blocking operations. Prefer java.util.concurrent alternatives like reentrant lock. Really watch out for pinning. Number 3, use the dedicated executor, executors.new virtual thread per task executor. It's designed for the common pattern and makes things simple. 4, don't forget thread safety. Shared data still needs proper synchronization, even with virtual threads. 5, monitor your application. Keep an eye on resource usage, memory, CPU, as you scale up the number of virtual threads. Don't assume infinite resources. 6, Leverage the compatibility, use the APIs you know, but be a bit cautious with very old or low-level libraries. Test them. 7. Get comfortable with debugging tools that understand virtual threads. IDEs are catching up, and tools like Visual VM can help. And maybe most importantly, number 8. Start small. Play with simple examples first to get a feel for how they behave before you redesign your whole production system.
Excellent. That's really practical advice. So let's recap. We've dug deep into Java virtual threads. The big takeaway seems to be that they offer a fundamentally new way to handle concurrency in Java lightweight, highly scalable, especially for I/O. They simplify the programming model for many common concurrent tasks, boost performance where threads wait a lot, and generally play nice with existing Java code. But not a silver bullet. You need to be mindful of CPU-bound tasks, actively avoid pinning, manage thread safety, and handle the potential debugging complexity.
Exactly. And if you step back and look at the bigger picture, virtual threads aren't just about tweaking performance. They really enable a different style of architecture for scalable systems. They make the simple one thread per request model viable at massive scale, something that was often impractical before. This lets developers focus more on the business problem and less on the complex plumbing of asynchronous code. It's genuinely exciting. I think we'll continue to see this reshape how server-side Java applications and microservices are built. Definitely something to keep learning about.
Couldn't agree more. Well, that brings us to the end of this deep dive. Thanks for joining us. And here's something to chew on. How might this shift, moving the burden of fine-grained thread management from you to the JVM, change not just the lines of code you write, but the fundamental architecture of the really responsive, highly concurrent applications you might build next? We'll be back soon with another deep dive.